Welcome to the Learning Assistant app YouTube channel. Have you ever wondered how a single carbon atom, which only has two unpaired electrons, manages to form four perfectly identical bonds in a molecule like methane? If we look at the standard blueprints of an atom, the math simply doesn't add up. To solve this mystery, we have to look at the strange and beautiful world of orbital hybridization. Let's start by looking at the ground state of a carbon atom. As you can see in this diagram, carbon has 6 electrons. 2 are tucked away in the 1s orbital, and the remaining 4 are in the second energy level. Within that second level, 2 electrons fill the spherical 2s orbital, leaving only 2 unpaired electrons in the dumbbell-shaped 2p orbitals. Now here's the problem. In chemistry, covalent bonds are formed when unpaired electrons are shared. Looking at this arrangement, carbon should only be able to form 2 bonds. But we know that in the real world, carbon is the backbone of life specifically because it consistently forms 4. To make this possible, carbon undergoes a 2-step transformation. First, notice how one of the electrons from the full 2s orbital gets promoted or excited, jumping up into the empty 2p slot. Now we have 4 unpaired electrons. But we're still not there yet. Look at the shapes of these orbitals. We have 1 sphere and 3 dumbbells oriented along the x, y, and z axes. If carbon bonded using these, the bonds would be lopsided and unequal. But nature loves symmetry. This is where the aha moment happens: hybridization. Imagine taking that 1s orbital and those 3 p orbitals and throwing them into a blender. We mix them together to create 4 entirely new hybrid orbitals. Because we used 1 s and 3 p orbitals, we call each of these an SP3 hybrid orbital. Watch what happens to their shape. Instead of spheres or dumbbells, we now have 4 identical lopsided lobes. Each one has a large region of electron density pointing outward. But since electrons are all negatively charged, they naturally want to stay as far away from each other as possible. As you can see here, to achieve the maximum distance from one another in 3-dimensional space, these 4 orbitals point toward the corners of a tetrahedron. This creates a perfect bond angle of 109.5 degrees. This isn't just a theoretical model, it's the reason why a diamond is so hard, and why methane is shaped the way it is. The key insight is that atoms aren't stuck with the orbitals they're born with. To achieve a more stable, lower energy state, carbon completely rewrites its own geometry. It's a beautiful reminder that in the quantum world, things aren't just one thing or another. They are often a perfect mixture of both.